we are investigating propagation of an electromagnetic wave inside a hollow pipe with rectangular cross section. We call that structure as rectangular waveguide. So, last time we defined certain conventions on the rectangular waveguide. This is the rectangular waveguide. The energy flows along the length of this pipe, and then we oriented the coordinate system such that the x axis is along the broader dimension of this waveguide and the y axis is along the shorter dimension of the waveguide, and then by definition we took this A which is greater than or equal to B, which is the height of the waveguide. And then by solving the wave equation, essentially we got the expression for the electric and magnetic fields, and specifically we investigated what is called the transverse magnetic mode, for which Ez is not equal to 0 and Sz is equal to 0, and then we have drawn certain important conclusions about this mode, which is transverse magnetic mode, and that was that without having the field variation in the transverse direction, you cannot have the transverse magnetic mode. So, we got transverse magnetic mode Tm Mn, where M and N give the indices in the broader and shorter dimension of the waveguide. So, the first index tells me the number of half cycles which are going to be along the x direction, which is along the broader dimension of the waveguide, and N tells me the number of half cycle variations along the shorter dimension, that is the y axis of the coordinate system. And then we saw that the Tm00 does not exist. That means, if I take M and N both indices 0, which means no field variation either in x direction or in y direction, that means no field variation in the cross sectional plane. If we take that situation, then these kind of fields cannot exist inside this rectangular waveguide. We also saw that not only that no variation in any direction, but even if the field is constant in any of the directions, either x or y, even then the field cannot exist. So, essentially what that meant was that we must have at least one half cycle variation in x direction and one half cycle variation in y direction for existence of the field. And that is what we got, what is called the lowest order transverse magnetic mode, which we got is Tm11 mode, which can survive on a rectangular waveguide structure. With this understanding, then we now want to investigate the other type of mode, that is the transverse electric mode, for which now since the field is transverse electric, the Ez is 0, but Sz is not equal to 0. And then as we explained last time, that using the observation which we have got from the transverse magnetic mode, that the tangential component of magnetic field becomes maximum on the surface of the conductor, and the field must have the sinusoidal variation in both the dimensions x and y. We can get an expression for Hz, that is some constant cosine of m pi x by a cosine of n pi y by b e to the power minus j beta z. Again, the m and n define the indices, that means the number of half cycle variations in the x and y direction, that means the broader and shorter dimension of the waveguide. So, as we did in the case of transverse magnetic mode, we can put these two indices along with Te. So, even the transverse electric mode is designated by Te Mn mode. I had also mentioned that this expression can be obtained again in a routine fashion. That means, you take this condition, substitute into the wave equation, solve for wave equation, get a general solution, find out the transverse component, match the boundary condition, and you will get the expression for the longitudinal magnetic field. Now, on the line similar to the transverse magnetic mode, we can ask what kind of indices are required for existence of these fields. So, firstly we can note that in this case, if m is equal to 0 and n is equal to 0, that means the mode is Te 0 0, the magnetic field now is not 0, it is constant. If you recall, in transverse magnetic case, the Ez was identically going to 0 when both the indices were 0, but in this case when both the indices are 0, this magnetic field does not go to 0, it is constant. However, if you recall, the transverse fields are expressed in terms of this longitudinal fields Ez and Sz, these are general expressions, but all these transverse field involve the space derivatives. So, either you have a derivative with respect to x or you have a derivative with respect to y. So, if I have a field which is constant, if it does not vary as a function of space, that is what m equal to 0, n equal to 0 would mean, that Sz is constant. Essentially all the space derivatives are 0, and that means all the transverse fields will identically go to 0. So, if we consider a situation that if m is equal to 0, n equal to 0, then Sz is constant, but since the transverse fields involve the space derivatives, all the transverse component of electric and magnetic field will identically go to 0. So, it will mean that E transverse and H transverse will be identically 0 because they derive the space derivative of the longitudinal component. So, that means in this situation when m is equal to 0, n equal to 0, we have the magnetic field, but there is no electric field because Ez was already 0 as we have taken by definition. So, we are having a magnetic field without having electric field, but what we have seen for time varying fields this cannot happen because time varying electric and magnetic fields are coupled. So, if this electric field goes to 0, then identically the magnetic field also must go to 0 because the time varying magnetic field cannot exist without electric field and vice versa. What that means is that in this situation this constant C must be identically equal to 0. So, in this situation the C must be identically equal to 0. That means the mode TE00 cannot exist now because this quantity is identically 0. So, these fields cannot survive inside the rectangular structure. So, we make a again important observation about transverse electric wave, that the TE00 mode cannot exist. So, we can write down now the observation for TE case, TE MN mode. Firstly, TE00 does not exist. Second conclusion now we can see from here that in case of TM case, when both the indices were 0, again the fields were identically going to 0. However, that is not true in this situation because if one of the indices is 0, then you have this function which will be non-zero. So, Sz will be non-zero and also it will be having a variation in space. So, if I take n equal to 0, the Sz will be a function of x. If I take m equal to 0, Sz will be a function of y. So, the space derivatives exist, Sz exists, so the transverse field exists, and that is why having one of the indices 0, the field can exist. That means TE M0 modes can exist, similarly TE0N mode also can exist. So, in this case we have important conclusion that the TE M0 and TE0N modes exist. That means now the field should have a variation at least in one direction. It may be constant in the other direction. That means if I take n equal to 0, that means the field will not have any variation in y direction and it will have number of half cycle variation depending upon the value of m. So, the field may be constant in one of the directions and it may be varying sinusoidally in the other direction. These kind of fields can exist now for the transverse electric case. So, if I now ask what are the lowest order modes which can exist, so we can get now the lowest order index. If I take M1 and N1, the lowest order would now corresponds to either TE10 or TE01. So, now we have got 3 lowest order modes. Transverse electric, if I take the lowest index M and N, I get TE10, TE01, and for transverse magnetic I have TM11. If I take this now magnetic field and substitute into the wave equation, or if I start with the wave equation, and as we did for transverse magnetic case, we got a dispersion relation, we will get identical dispersion relation in this case also. So, in this case also, as we got in case of transverse magnetic case, we will get this quantity h square, that will be m pi by a whole square plus n pi by b whole square. And as we got in the previous case, the phase constant in the z direction, which is beta, that is omega square mu epsilon minus m pi by a whole square minus n pi by b whole square, square root of this quantity. In parallel plane waveguide, we had called this quantity beta bar. However, in this case, since the net wave propagation is going to be in the z direction, just for simplicity we have dropped the sign bar, but in this case beta essentially means the phase constant in the z direction or along the waveguide. Now, as we define the cutoff condition in case of parallel plane waveguide, the same thing we can define in this case also, that all the E and H field variations which we have, they vary as e to the power minus j beta z. So, it will represent a travelling wave provided this quantity beta is a real quantity. If I take a frequency for which this quantity is greater than omega square mu epsilon, then this quantity inside the square root will become negative and beta will become imaginary. If beta becomes imaginary, then this quantity does not represent now a travelling wave, it will simply represent exponentially decaying fields in the direction z, that means along the waveguide, and essentially the wave propagation will cease. So, for propagating wave, it is essential that the frequency must be higher than certain value, so that this quantity is a real quantity. As we discussed in case of parallel plane waveguide, at a frequency where this transition takes place, that means from the travelling wave to the decaying field, we call that frequency as the cutoff frequency of a mode. So, as we can see, for different values of m and n, we will have different frequencies where this transition will take place, and the transition will take place essentially when beta is equal to 0, this quantity is equal to 0. When it is positive, you get beta real, so you get a travelling wave. When this quantity is negative, you get beta imaginary, so you get a decaying field. So, we define now this condition, what is called the cutoff frequency of a particular mode, and that frequency is the frequency at which this quantity becomes 0. So, let us say this cutoff frequency is given by omega c, angular frequency, or this is 2 pi into the cutoff frequency f c. So, by substituting this omega c inside this, essentially I get omega c square mu epsilon, that is equal to m pi by A whole square plus n pi by B whole square. I can write down explicitly for the frequency. So, I get the cutoff frequency f c, that will be 1 upon 2 pi square root mu epsilon m pi by A whole square plus n pi by B whole square root. So, now knowing the mode order, that means knowing the value of m and n and the dimension of the waveguide, I can find out the cutoff frequency for a particular mode. The dispersion relation now can be written in terms of this quantity, because this quantity is nothing but omega c square mu epsilon. So, many times we can write the dispersion relation, which is beta is equal to square root of omega square mu epsilon minus this quantity, which is nothing but omega c square mu epsilon. So, we can write this as omega c square mu epsilon. We can take this omega square mu epsilon common. So, this will become omega square root mu epsilon 1 minus omega c by omega whole square, or I can write in terms of the cutoff frequency. Now, noting that this quantity square root mu epsilon is 1 upon the velocity of the wave in the intrinsic medium. So, if I consider a medium which is filling the waveguide has permeability and permittivity mu and epsilon, then the velocity in that medium intrinsically will be 1 upon square root mu epsilon. So, this quantity is nothing but the velocity of light in that medium which is filling the waveguide. So, we have here omega divided by c 1 minus, and I can write omega explicitly in terms of the frequency. So, this will be cutoff frequency by frequency square root. And omega by beta, if you write this is omega is 2 pi into frequency, and then c upon frequency is the wavelength in the intrinsic medium. So, this quantity we can also write as 2 pi by lambda into 1 minus cutoff frequency by frequency whole square. This is your phase constant. Now, this is the phase constant for the waveguide in the z direction. So, now imagine that I have this structure for which the quantity which I can measure is the variation of the electric field along its length. That means, if I take some probe and move along the length of the waveguide, I will see the separation between 2 points, 2 maximas, which will be separated by a certain distance, and that will be related to the phase constant of that wave along the direction of the waveguide. That means, this quantity beta, whatever we have here for this particular mode, this quantity is 2 pi divided by lambda, which I am going to measure on that waveguide. This lambda is certainly not same lambda which intrinsically the wave has in an unbound medium. That means, if I know the properties of the medium mu and epsilon, and if I imagine this medium to be infinite, then I get a wavelength what is called lambda, which is the velocity of light divided by the frequency. However, if I take a structure like a waveguide, certainly I am not going to measure this lambda anywhere, what we are going to measure is this phase constant or an equivalent wavelength which will be related to this beta, which is the phase constant. So, we know by definition that if I know the phase constant, I have this quantity beta, which by definition is 2 pi divided by wavelength, but this wavelength now is not the wavelength in an unbound medium. This is the wavelength which we are going to measure along the length of the waveguide, or this is the wavelength which is for that guided electric and magnetic field distribution inside the rectangular waveguide. That is the reason we call this wavelength as the guided wavelength, and we put a suffix to this as G, where this quantity is called the guided wavelength. So, see what we have done, we got this quantity beta from our analysis. Whatever that quantity beta is, if I take 2 pi divided by that beta, we get a number, and that number essentially tells me the effective wavelength along the waveguide in which the wave is going to travel. So, on a physical structure like a rectangular waveguide, the meaningful parameter is the guided wavelength and not the intrinsic wavelength, because this wavelength we are not going to measure right in along the waveguide. Once I do that, then I can substitute for beta as 2 pi by lambda, and then that can be related to the intrinsic lambda as lambda g, that will be equal to lambda divided by 1 minus fc upon f whole square root. Few things now can be observed from here. This is the wavelength of wave in an unbound medium. This is the wavelength which you are going to measure inside this bound structure along the waveguide, and for travelling wave the frequency has to be greater than the cutoff frequency. So, as the cutoff frequency, first thing we notice here that this quantity is always going to be less than 1 for a travelling wave, and therefore, the guided wavelength is always greater than the intrinsic wavelength in that medium. So, first thing we see is the guided wavelength is always greater than lambda, intrinsic wavelength in the medium. As the frequency tends to infinity, this quantity will become 0, and that time this lambda g will approach lambda, but this will never become equal to lambda, because you will always have a frequency which is finite. So, this quantity will be always a finite quantity, and this quantity will be always less than 1. So, we do not have for a guided structure, no matter what frequency we operate with, we will never have the guided wavelength equal to the intrinsic wavelength in that medium. Second thing what we note from here is that as the frequency approaches the cutoff frequency, this quantity tends to 1 and wavelength becomes larger and larger, and at cutoff frequency the wavelengths become infinite. So, second important conclusion we get is lambda g, which is the guided wavelength, it tends to infinity when the frequency approaches the cutoff frequency. Now, knowing this value of beta, we have seen for parallel plane waveguide, and same thing is true in this case also, that omega by beta gives me the phase velocity, and now the phase velocity will become function of this fc upon f. So, when fc upon f is much smaller compared to 1, that time the phase velocity will approach the intrinsic velocity in the medium. Otherwise, when the frequency approaches the cutoff frequency, again the phase velocity will become infinite. Same thing is happening here, that the frequency multiplied by lambda g, that gives me the effective velocity of wave on the structure. So, when frequency is much larger compared to fc, the velocity approaches the intrinsic velocity c, and when frequency is approaching cutoff frequency, then the velocity tends to infinity. So, since in this case lambda g tends to infinity, the velocity of the wave, which is lambda g into frequency, that also would tend to infinity. So, these are certain important conclusions we can draw for this wave, which are valid for transverse electric as well as transverse magnetic case. Now, come back to the field expression again and try to now investigate the relative cutoff frequencies for different modes, and we have seen now that there are three modes which we can call as the lowest order mode. One is TE10 mode, TE01 mode, and TM11 mode. So, we can take mode here TE10, we can take TE01, and we can take TM11. These are the lowest indices are possible for the TE and TM modes. The cutoff frequency for TE10 mode would correspond to N0 and m equal to 1. So, the cutoff frequency will be 1 upon 2 pi square root mu epsilon. So, if I write down cutoff frequency for this, this will be Fc TE10, that will be equal to 1 upon 2 pi square root mu epsilon into pi upon a, because n is 0, m is 1, into say pi upon a. The cutoff frequency for this mode TE01 mode will be Fc TE01, that will be pi upon b divided by 2 pi square root epsilon. So, this will be pi upon b upon 2 pi square root mu epsilon. And for TM11 mode, both of these m is 1, n is 1. So, for this mode you will get the cutoff frequency, which will be Fc TM11, and the same cutoff frequency will be for TE11 also, that will be equal to 1 upon 2 pi square root mu epsilon pi upon a whole square plus pi upon b whole square square root. Now, recall by definition we have a greater than b. So, if we are not considering square waveguide, where of course these two quantities will become equal. Otherwise, for a rectangular waveguide, since a is always greater than b, this frequency is smaller than this, and this frequency will be smaller than this, because you are having here now both the terms pi a and pi b. So, in general, if I take these three modes, essentially I got the cutoff frequency Fc TE10 is less than the cutoff frequency for TE01 is less than for the cutoff frequency TM11. And we have seen the mode TE00 or TM00 do not exist. That means this is the lowest frequency which can propagate on the structure. That is the absolute minimum frequency which the structure will support. So, whenever we try to excite a rectangular waveguide, the possibility of exciting this mode is the highest, because if at all the energy is going to propagate, it will be propagating at least in this frequency. It is possible if the frequency lies between this and this will propagate, but others will not propagate because they will be below cutoff. If the frequency lies somewhere here, then these two will propagate, this will not propagate, and so on. But this is the lowest frequency which the waveguide is capable of supporting. That is the reason this mode, the TE10 mode, is the important mode for rectangular waveguide. And this mode therefore is referred to as the dominant mode of the rectangular waveguide. So, we introduce this word, what is called the dominant mode, and this mode essentially means TE10 mode. So, this one has now the first index 1, that means this has a half cycle variation, fields have half cycle variation in the x direction, and the field is constant in the y direction. That is the mode which is going to propagate inside the structure. And since this is the important mode, because if at all energy propagates is going to propagate in this mode, we can have a little more detailed analysis of this mode rather than talking about a general mode of TEMN or TMMN. One thing may also note, so since the cutoff frequency expression is this, depending upon the value of A and B, it is possible that the TE01 mode may have a frequency which is lower than or higher than the TE20 mode. I can have the frequency which is TE30 mode, where TE03 mode could be lower than the TM11 mode or TE11 mode. So, depending upon the dimension, the ratio of A and B, it is possible that the higher order TE modes like TE20 or 30, they may have cutoff frequency smaller than TM11, or they may have a frequency more than that. So, one cannot make any general statement about what is the order of the cutoff frequencies for the various modes of TEMN or TMMN. However, one thing is absolutely clear, that the lowest frequency is always TE10 mode. Beyond this, I cannot tell what the cutoff frequencies would be, what will be the order of cutoff frequencies, but this is the frequency which is always going to be lowest. That is the reason, if we wanted to have the single mode operation inside a waveguide, and we will see later why single mode operation is desirable inside the waveguide, the energy will always propagate inside this dominant mode, which is TE10 mode. So, that is why we now make little detailed investigation about the TE10 mode. So, first thing, we can now write down the fields for TE10 mode. So, essentially we get the field expression for the SZ, substitute now m equal to 1, n equal to 0 in this. So, we get SZ for TE10, and then substituting in the transverse field expressions, we can get the remaining components for the TE10 mode. So, for this case, the Hz now is equal to the constant times cos of m equal to 1. So, you substitute m equal to 1 here, it will be pi upon a into x, this quantity is 0. So, this is 1. So, this will be pi x by a e to the power minus j beta z. So, the first of all note here, the Hz is only a function of x, that means the derivative of Hz with respect to y is 0. So, I have here the component Ez is already 0 for TE case. So, this thing is not there. We are having here for Ex the derivative of Hz with respect to y, and this is not a function of y. So, this quantity is 0, that is why Ex is 0 for this mode. So, we get the Ex is equal to 0 for this mode. Similarly, we can see again Hz has a y derivative with respect to y, that is for Hy, So, this quantity also will be 0. So, for this mode the Hy will also be 0. So, the quantities which we will have now for this field is the field which is Ey. Now, the H in this case, since we have taken m equal to 1 and n equal to 0, the H which we have got, which is this m pi upon a whole square plus n pi upon b whole square, n is 0, m is 1. So, H is pi upon a. So, for this we have H is equal to pi upon a. So, I can now substitute into this and I can get the Ey component, which is j omega mu upon h square, which is pi upon a whole square. So, that is j omega mu upon pi upon a whole square dhz by dx. So, if I take this will give me c minus sin pi upon a sin of pi x by a e to the power minus j beta z. And I will get a component which is Hx, Hy is 0. So, Hx component will be equal to j omega epsilon upon pi upon a whole square, this quantity with a minus c pi upon a sin of pi x by a e to the power minus j beta z. I can simplify and get the field expression now explicitly for the TE10 mode. So, TE10 mode has only one electric field component, that is Y, and two magnetic field components Hx and Lz. So, now we have the fields for TE10 mode. So, we get Ex, Ez equal to 0, Ey equal to, I can just simplify this, 1 pi upon a will cancel. So, this will be minus j omega mu a upon pi into c sin pi x by a e to the power minus j beta z. Hx will be equal to minus j omega epsilon a upon pi c sin pi x by a e to the power minus j beta z. Hy is 0 and Hz is equal to c cos pi x by a e to the power minus j beta z. So, these are now explicitly the field for the dominant mode of a rectangular waveguide, and normally we operate this waveguide in this mode TE10 mode, because as I mentioned many times we have a requirement that there should be single mode propagation on this waveguide, and the single mode propagation will take place in this mode, which is dominant mode. So, these are the fields which are essentially going to exist on this waveguide. The cutoff frequency as we talked about and the cutoff wavelength which we talked about, we can calculate now the cutoff wavelength for this lowest order mode or the dominant mode. So, I can go back and substitute into the expression for the wavelength and get the cutoff wavelength from here, and I can calculate the phase constant and the guided wavelength of this field on the waveguiding structure. So, physically now if I look at how the fields are, firstly the rectangular waveguide cross section if I draw like that, the electric field is having only y component and this is the y direction, this is x direction and z direction is going inside the plane of the paper. Electric field is y oriented, which is this, and it is having one half cycle variation. So, it is maximum here, 0 here, 0 here, that is what the sign function is telling you. So, a field here which is maximum at a by 2, x equal to a by 2, at x equal to 0 and x equal to a, this field go to 0. So, the Ey will be 0 here, it will be maximum here, it will be 0 here. So, if I draw that variation, this variation will be one half cycle variation. In this direction for Ey, and there is no variation for this field in the y direction. So, the field varies in x direction by half cycle and no variation in y direction. So, if I want to represent this field now in terms of the vectors or the arrows, then here the arrows are large or the field is very large here, and in this direction the field is constant. So, they have same size of vectors. If I go now in this direction, the field decreases. So, here I will get like that, like that. If I go still further, I will get like that, and if I come here, it will become 0. Same thing is going to be on this side. So, here I will get the field which will be like this, go further, and when I go to the wall, it will become 0. So, if I take now the electric field and if I measure it here, we will get the maximum electric field at the center of this waveguide. Direction will remain like this, and the field strength everywhere on this line will be same. Similarly, if I move here, it will be same, only thing this will be smaller compared to this, and as I move now towards the walls, this component which is tangential component to these walls will go to 0. So, this field will become 0 here, this will become 0 here. We can now visualize this field, and we will see a little later a little more detailed visualization of these fields in different waveguiding structure. But at this moment it appears that this field is maximum at the broader wall of the waveguide. So, if I take this structure waveguide like this, then this field is going to be maximum here at this broader wall of the waveguide. Same thing essentially will happen to the other modes also. So, if I take the higher order modes, again you will find the locations where the electric and magnetic fields will be maximum. Why this information is important is that one may ask a question that once the waveguide is given to you, how would this particular mode get excited inside a waveguide? Do I have a mechanism by which a particular mode can be excited, or will the waveguide simply decide the excitation of the modes? Can we selectively excite certain mode inside a waveguide? And by looking at the field distribution, essentially that becomes clear that yes, if you create a mechanism by which the field will be maximum at this place, then that excitation mechanism will support this field which is maximum here, and then the mode which will get excited inside the waveguide will be TE10 mode, provided the size of the waveguide is such that the TE10 mode propagates on the waveguide. So the two things are required. Firstly, the size of the waveguide should be large enough so that the frequency is greater than the cutoff frequency for that mode. Secondly, the excitation mechanism should be such that the field or the mode which you want to get excited, those fields match with the excitation. So if I take a field distribution for which the field was 0 at some location, if I try to put the excitation there, obviously the mode will not get excited because the field for that mode is 0 at that location. So even if you provide excitation at that point, there is no excitation of the field inside the waveguide, because at that location this mode has an amplitude 0. So for excitation of TE10 mode, normally what we do, we put some kind of a probe here which goes inside the waveguide on the broader wall at the middle of that, and because of that you have the fringing fields. Now the mode which we talked about, these are the field distributions which satisfy the boundary conditions. Now here we are exciting the field which is a sudden change of electric field at that point. Then one can show that to satisfy the boundary conditions here for the field, you require all possible modes of the waveguide, whether they are travelling or decaying, because these are essentially telling you the orthogonal functions which satisfy the boundary condition inside the structure. So locally around this probe, all kinds of mode will get excited inside this waveguide, including the field which are decaying fields. Only as we travel further in the waveguide, those fields which are below cutoff, they will be dying down rapidly. Only that frequency for which the cutoff frequency is less than the frequency of this will travel, and if you make sure that that frequency is larger than the cutoff frequency of TE10 mode but smaller than any other cutoff frequencies, you get a guaranteed mode of TE10 inside the waveguiding structure. So essentially a TE10 mode inside a waveguide can be excited by putting a probe which can excite electric field inside the waveguide at the middle of the broader wall. So in practice, whenever we do the experiment or we carry the high frequency signals like microwave signals, these signals are carried by a rectangular waveguide, and this rectangular waveguide always operates in a mode which is the dominant mode, which is TE10 mode. One can now ask a question. I have been repeatedly saying that we should operate this waveguide in a single mode operation. There are many applications where we want single mode operation. Question one can ask is, why do we want single mode operation? And the answer essentially lies in our dispersion relation. So we go back to our dispersion relation, which says now the phase constant is a function of m and n, and since the phase constant is a function of m and n, the velocity of this mode also will be a function of m and n. What that means is that for a given frequency omega, the different modes are going to travel with different speeds. Now if you want to send the information on this waveguide, then we will try to put the energy inside this waveguiding structure, and then if large number of modes can be supported by the waveguide, if the waveguide does not have single mode operation, the energy will get distributed into various modes, that means various combinations of m and n. Each mode will have its own velocity for travelling. So as they travel, the energy which is going on different modes essentially separate out. The phase relationship between different modes is broken. Now imagine a situation that we transmit a signal which is not sine wave, sinusoidal signal, we transmit a pulse at high frequency. Now if the energy is divided into different modes and different mode travel with different speed, when the energy reaches on the other side, other end of the waveguide, all the mode energy will not reach at the same time. That means the energy packet which we send will not appear like a packet, it will be distributed in time, because some mode will arrive earlier, some mode will arrive later. So the dispersion phenomena which we talked about essentially will give me the broadening of the signal in time as it travels on the waveguide, and this is happening because energy is getting distributed into various modes and various modes travel with different speed. To avoid this, we try to put the energy only into one mode, so that the energy remains in that mode, and then the distribution of energy or differential delays which come because of the multimodal mode propagation inside the waveguide is avoided, and we do not have broadening of the signal when it travels on the waveguide because of the multimode propagation. This is the aspect which essentially one has to make use of when we design the waveguides at high frequencies. So just to conclude, for a rectangular waveguide, the important mode is the transverse electric mode, TE10 mode. That mode we also call dominant mode, because it has the lowest cutoff frequency, and for this frequency, if we make sure single mode propagation takes place over a certain range of frequencies. So in experiment we make sure that the frequency lies in that range, so there is a single mode propagation.